So now that we know about similar polygons, today we're going to talk about similar triangles and how do we know when triangles are similar. And there are some rules, there's some shortcuts that we can learn that will help us out. So our goal today is to prove that certain triangles are similar by using these shortcuts. And one shortcut is angle-angle. We have a side-side-side similarity shortcut, just like we had one for congruent triangles. So there is a side-side-side that works for similar triangles, and a side-angle side, which we also had for congruent triangles, but we can also show that triangles are similar using side-angle side. And then the last thing we're going to do today is use triangle similarity to solve problems. So if we know triangles are similar, what can we conclude based on that fact? So the first thing I want you to realize is that if I have all the angles of one triangle are congruent to all the angles of another triangle, the triangles are similar. So they can be different sizes, but the angles are the same, the shape stays the same. So if all the angles of one triangle are congruent to all the angles of another triangle, so this angle is the same as this angle is the same as this, and this angle is the same as this. As long as that's true, no matter what the side lengths are, they're going to be in proportion, and the triangles are going to be similar. So these triangles are similar because all the angles are, corresponding angles are congruent. So knowing that if three angles, corresponding angles are congruent in a pair of triangles, that the triangles are similar, do we need to know that all three are congruent? And we don't, because remember we have that theorem that says that if I have two pairs of corresponding angles in a triangle that are congruent, that third angle, so angle C and angle F, they also have to be congruent because it's called the third angle theorem. And so by that, I know that all three angles are congruent. Therefore, that this pair of triangles, triangle ABC, okay, and so now it's important again how we name them. So if I look at this, I have triangle A that's got one tick mark, and I'm going B and C, then I have to go the same way, D, E, C. So triangle ABC is similar to triangle DEC. And remember, it's important the way you name them because writing this similarity statement implies that angle A is congruent to D, angle B is congruent to E, angle C is congruent to, well, I wrote C and it should be F, shouldn't it? So let's fix this. Is congruent to F. And so triangle ABC is similar to triangle DEF. And this is called the angle-angle postulate. The angle-angle postulate, what does it say? It says that if I can show that two angles in one triangle are congruent to two angles in another triangle, then I know the triangles are similar. Okay, so here we have a pair of triangles, and they're asking us to show using that A similarity postulate, angle-angle similarity, that these are similar triangles. So all I need to do is show that two angles in this pair of triangles is congruent. So I look, and here's a right angle, here's a right angle. Well, all right angles are congruent because they're all 90 degrees. So that is one thing I could say. And then notice we have this friend of ours, this vertical angle pair, and we know vertical angles are also congruent to each other. So there we go, two angles that are the same. I'm going to make the conclusion based on the fact that the right angles are congruent to each other, the vertical angle pairs are congruent to each other. So let's go ahead and write that out. So I'm going to say angle A is congruent to angle D. Now it didn't say we had to say why, but we know why. It's right angles are congruent to each other, right? So if I was doing a proof, I would need to write the reason. So I'm just sketching it down. They didn't tell you had to. And then for the other angle pair, now we're going to be careful about how we name these because order is important. So I say, I'm going to start at the right angle and say ACB. And I'm going to start at this right angle and say DCE. So we're going to say, all right, so angle ACB is congruent to angle DCE. And why? What's the reason? Again, it didn't tell you to write the reason down, but let's do it. Vertical angles. Vertical angles are congruent. And so our conclusion is this, that um, by angle similarity, remember similar is just that one squiggle, triangle ACB is similar to triangle DCE. I don't want to make it look like this angle is similar to this, but this is my reason here. I'll, I'll highlight the reason. The reason is right here in green, and then my actual statement is this. So this is my conclusion. I can conclude that those are similar triangles because of the angle similarity. Now, when we were doing congruence, we had a side um, theorem that said if three sides of one triangle are congruent to corresponding sides in another triangle, then the triangles are congruent to each other. There's a similar theorem, and this is based on the side similarity. Okay, and so similarity means that the sides are in proportion, they're not the same. So we're not talking about congruent sides, we're talking about sides that are proportional to the other sides. And so if I know that if I take these sides and I'm going to relabel these sides so that so they can do it. I'm going to call this side C. Oops, I got the wrong pen. So we want this. All right. So if I'm going to label this side C, this will be side A, this will be side B. It's common when you're labeling sides. You notice small c is opposite big C, small a is opposite big A. So that's a very common way to name things. Got small d, small f, small e. So the small letters are the side lengths, and the large A's are of course the vertices. So what am I saying here? I'm saying that if I know that the sides are in proportion, so notice that C is corresponding to F. So if I know C over F is equal to B over E, which is equal to A over D, if those sides are in proportion, they make the same fraction, the same decimal, the same number, then I can conclude that triangle ABC is similar to triangle DFE. Actually, I did that wrong. So here's an important thing to be careful of, because I just did the exact same thing that I should not do. I'm naming this ABC. Why did I do that? Because I went in order of the letters. So I didn't need to, but I did. But if once I did that, I have to name this other triangle DEF. I have to go in that order. I can't go backwards. So what I wrote there is incorrect. So you be careful. Don't do as I say, not as I do, I guess. So this is triangle DEF. Okay, I fixed. So triangle ABC is similar to triangle DEF. This is called the side similarity theorem, and we can use that as a reason, a justification for saying that two triangles are similar. So here is another theorem that we can use, and this theorem has to do with two sides and the included angle between them. So if two sides of one triangle are proportional to two sides of another triangle and their included angle is congruent, that is enough to show that the triangles are similar. So here, if we look, you can see that the included angle B is between the side AB and BC, and they're saying that AB is proportional to DE in the same proportion as BC is to EF, and the included angle is congruent. So these are similar triangles. So I'm gonna rename the sides like I did last time. I'm gonna say this is A, B, small c. This is D, F, and E. And so what I would need to show here is I would need to show that C to F, that proportion, or that ratio rather, is going to make a proportion that is true, and that's going to be equal to A over D. And so that proportion being that that's true, that those ratios are the same of the sides, and angle B, I know, is congruent to angle E. Given that information, we can conclude that the two triangles, triangle A, B, C, is similar to triangle D, E, F. Okay. So I learned from my mistake. I was careful about the order this time. So here's an example, and we have two triangles. We have triangle PRQ, and we have triangle STU. And I'm not sure if, which order to do it in other than that they wrote this here. I mean, I'd have to look at it carefully. PQR and STU show that they are similar. All right. So first of all, as we look at this, we don't see any angles that we know, right? So there's no information about what these angles are. So I'm probably not going to use the side angle side. I'm probably going to be using side similarity. So the plan is I'm going to see if all the sides are in proportion. And so we're going to mark the sides first of all so we can match them up. So here is the smallest side. It's 2 and 3, right? So they need to go together. And the other sides are, it looks like they're isosceles triangle. So these are going to, I'm going to think of just flipping PQR upside down. And so this angle here is going to go here. Now it really doesn't matter because they are the same length, but this is the way I'm going to match them up. And so here we are, and let's see if we get the same ratio. So I have, I'm going to go from the small to the large, and so I'm going to go 2 over 3, and I'm going to show that that is equal to, I don't know yet, so I'm going to put a question mark. I'm going to show that that is equal to 3 over 4.5. Now, I also have to show that it's equal to the third side because there's 3 sides, but these are the same. 3 over 4.5 is the same. So we know that's equal for sure. We're not sure about this. So how are we going to tell that? We can use a calculator and get the ratio. And sure enough, when we divide these, 2 divided by 3, that's going to give me let me use a different pen. So that's going to give me 0.6 repeating. And if I take 3 divided by 4.5, that's also going to give me 0.6 repeating. And so changing them to decimals and checking, I can tell that these are indeed, this is a valid proportion. And so I can conclude by side similarity theorem that these are in fact similar triangles. And so I'm going to write my similarity statement. So my similarity statement is going to be triangle PQR is similar to triangle STU. I should point out that you could just use fractions as well to do this. So if I want to see if this is 2/3, I can rewrite this as 30 over 45. So multiplying the top and bottom by 10. And then dividing this out, 15 goes into 30 twice, 15 goes into 45 3 times. So we could also just verify it using fractions. So this time when I'm looking at the example, they're asking to do the same thing, verify the triangles are similar to each other. And I can see that I have an angle this time, and it's included between the 2 sides that I know. So I can be pretty sure that what I'm going to be trying to use is the angle side similarity. So I need to show that the 2 sides that I know make a valid proportion. And so I'm going to take this short side and match it up with this short side, the longer side matching it up with this longer side, and I have the angle included in there. So the first thing that I do know for sure is I know that I have the included angle. I know angle D is congruent to angle H, Why do I know that? Because they tell me they're both 70 degrees. So that is given. So the angle part is taken care of. So I just have to match the sides up and verify that they make a valid proportion. So it doesn't matter which way you go, from the large to the small or small to the large. I'm going to put the large one in triangle DEF in the numerator. So I'm going to do 5.8, and that is going to be over 2.9. And this is going to be equal, I don't know, I have to check, so I'm putting a question mark there, over 2 over 1. So I know that if I divide 2 by 1, I get 2. So if I divide 5.8 by 2.9, do I get 2? Well, we can quickly check. So I'm going to take 2.9, I'm going to double it, and see if I get 5.8. And this is 18, 4, 5, and I do. So we've verified that this is, in fact, valid. I don't have to have a question mark. I know that that is true. So we know that the sides are in proportion and the angle is in fact congruent. So we can make the conclusion that triangle DFE, so I didn't name it the way they did, but you could. It doesn't really matter, just so we name them correctly. So I did D, F, and E. So when I name the other one, I have to start at the same angle. So I'm going to start at the 70-degree angle, and I'm going to do HKJ. So it's similar to triangle HKJ. Now, it would be perfectly okay to name it in other ways, but just so the corresponding angles match. Okay, so here we have a situation where they're asking us to write a proof. So the only difference between verifying and writing a proof is that we just have to justify each of our steps. And just as I look at this picture, notice we have a pair of vertical angles. So I'm suspecting that we're going to shoot for side, angle, side for similarity. We could do angle, angle if we had the information. We could do side, side, side. Um, this seems to be because of the vertical angles. I'm guessing that's the first thing we're going to do. So let's look at the information they gave us, and they tell us these two things. They tell us 3UT equals 5RT, and 3VT equals 5ST. So if I'm using side angle side, I have to show that the sides make a valid proportion, the ratio of the sides. And so in order to do that, I need to get the numbers on one side and the lengths on the other side. So here we have a 3UT, so I want the 3 to stay there, but I want to get rid of UT. And I want the 5 to come over to this side, and I want the UT to be over here with the RT. And so we're going to divide to do this. So first of all, this first step, the reason is given. Okay, they told us that this was true. It came right from up here. It's given. And so the next thing we're going to do is I'll use a different color pen. I'm going to divide by 5 UT. Doing that brings the 5 over to the left side and gets rid of the UT over to the other side. So I got to divide the same thing on both sides. And similarly, when I go to the second thing that they told us, I want to divide by 5 VT. Right? And doing that allows me to divide out the UT, that gives me 1. Divide out the 5s, that gives me 1. The VT divided by VT, that's 1. And 5 divided by 5, that's 1. And so at this point, we now have 3/5 equals RT over UT, and 3/5 also equals ST over VT. So we have those two proportions. And what's the reason for that? What did I do when I did that step that's in blue? I divided both sides by the same amount. That's called the division property of equality. That allows me to do that. And so that's what the reason that I could do that blue step there. Maybe I would highlight this in blue. So this is blue, right? Now, what I want to show is that RT over UT is equal to ST over VT. And we can do that by substitution, right? So I can say they're both equal to 3/5. So RT over UT equals ST over VT, which they're both equal to 3/5, right? Um, Whether you said substitution or transitive property, I think either of those would be okay. And so these are by substitution, right? And so what we've shown here are that the sides are in proportion. So let's look at the sides on the triangle. So if I look at this triangle, I can see that RT is matching UT. So RT and UT go together, and the ST and VT go together. And so we have we've shown that the sides are in proportion. What we need to show is that the included angle is congruent, and we know that's true by vertical angles. So let's make that statement. I'll use a red pen. So I'm going to say angle STR is congruent to angle VTU. And what's the reason? Vertical angles are congruent. So this is my reason. And so the conclusion now is, therefore, triangle UVT is similar to triangle RST. And why? By side angle side similarity.